Okay, so this is going to be a bit more of a in-depth look at the features built into Wiggle with respect to a typical cryoDRGN analysis. So one of the very first things that you need to do, which I've already done here, is embed your latent space using a dimensionality reduction technique such as principal component analysis, UMAP or TS&E. Some of these are slower than others, and for this video I've just done principal component analysis. You can also subsample this space, and this is useful because when you're rendering, say, 100,000 points, the interactivity of this space becomes a little bit more laggy. And so if you want to try and look at 1,000,000 points, then you're going to have a hard time. But at the same time, you can't really click on 1,000,000 different points in your coordinate space and look at every single volume associated with those. So maybe rendering a full 1,000,000 particles is not really meaningful. So let's bump this up just for the sake of it to 50,000, and we'll run the principal component analysis again. You can change that and rerun the dimensionality reduction if you like. Now that that's run, you can see here that if I scale with the right click, I'm holding down the right click button and just dragging the mouse up and down or left and right. If I right click, I can also export an image. So you can see that there are obviously different clusters here, and these are well-known clusters that correspond to different assembly state intermediates for this particular ribosome. One thing to note in Wiggle is that if you want to get very rapid feedback between these points in your latent space and a confirmation of volume here in Chimera, you may not necessarily need to render this at the full pixel size and full box size. So if I just bring the log down here so you can see what's going on. At the moment, this volume is downsampled to 128 pixels, and then I crop it to 96. So this is quite useful if you want to speed up your analysis. So if I just look at the box, I can tell here immediately that actually I can crop this more aggressively, maybe down to 70. And as I change that and hit enter, cryoDRGN automatically updates. So that may be suitable, but I may accidentally chop off components of the small subunit. Let's just have a quick look. Yeah, okay. So here you can see it's chopping it off. So maybe let's stick with 96 for now. You can see that the volume rendering from cryoDRGN is relatively fast. Actually, it's still chopping it off a little bit, so let's maybe bump that up to 100. Okay, I think that's good enough. So it's relatively fast to generate a volume from cryoDRGN as you click through this space. Keep in mind that cryoDRGN is doing a full pass through the model. If you have a faster GPU, this is just a GTX 1080, so it's a little bit slow. This is even faster. But it is worthwhile just downsampling your volume maybe by a factor of 2 and then cropping it. And the same applies for CryoSpark, which I'll show in another video. Now in this particular case, the volumes are Z-flipped. That might not be obvious to you, but I know for a fact that this particular analysis, the volumes are all Z-flipped. So if you turn on Z-flip all output and we re-render that same volume, this time it will be in the opposite hand, which is useful if you've done your full cryoDRGN analysis or someone's done their full analysis in the wrong hand. So various tools are available to us. Obviously we can change the way that we visualize this landscape. I prefer the night mode because I tend to burn the midnight oil and it hurts my eyes. This is mostly just aesthetics to help you inspect your landscape. You can change the point size if you need. So let's have a go at clustering it's doing a cluster analysis with cryoDRGN, so I'm going to close that. There are different clustering analyses available. Some of them work better than others, and I may remove some in the future. I like this Gaussian mixture method. It tends to do a really good job. I'm just going to ask it to generate 10 clusters and try and split this landscape up into 10 clusters. And I also wanted to generate a random volume from each of those clusters, and then I want Chimera to color those according to the color of the cluster. And here we can choose different color palettes to color those clusters by. So I'm just going to use Viridis for now. So if I say go, wiggle, you can see it's busy clustering those points. It doesn't take too long depending on how many points you're actually showing. And then once it's done, I can hear my GPU whirring at the moment, so it's finished the clustering and it's now grabbing a volume from every one of these clusters, and in a brief moment it will display these. Okay, there they are. Now at the moment they're transparent, and that's because I had this transparency feature turned on, but we can just switch that off in Chimera to make it easier for us to see. Okay, so all of those volumes are colored according to the clusters in this space, and we also now have different clusters which we can toggle on and off in order to inspect them independently. So if I just turn them all off except for the first one, it might be easier if I turn the transparency off. That's the first cluster, which corresponds to the first volume in this list. Let's just change the lighting to make this a bit easier to see. So that looks like, I don't know much about ribosomes. This is just some intermediate component. And as we look through these volumes, we can see that different subunits get added on. So from cluster 1 to cluster 3, or cluster 0 to cluster 3, and cluster 1 to cluster 4, you can see that there's this additional component which is present in this cluster. So this just allows you to quickly get a sense of what each cluster corresponds to. Obviously within a cluster there may also be variations, so if we just choose this one for example, and we make sure that our interactive continuous update is switched on under clustering, if we just have a click through this space, what we might see is that there's actually variation within this space. So there's, that volume looks a little bit different. And this makes sense because in theory, all conformations that are identical should superimpose in this space. They should all have the same latent coordinates for them. So the fact that these are slightly different means that there may be slight variation amongst them. Okay, so that's the clustering. You can switch all these back on. Perhaps you might find a subset that is interesting to you, and you can look at that in more detail. I'm just going to briefly turn all of these back on. You can toggle these on and off if you like, if you want to go back to the non-cluster view. Let's just keep it off for now and keep the transparency on. And they're a bit too large for me. I'm going to drop them down and make them a bit smaller. That helps me see that there's one cluster there, maybe another one there, one there, two. So what are we up to? 4, 5. That looks like a 6th one, a 7th one. Under graph traversal mode, what you can do is either sample along each latent coordinate, just taking 2 standard deviations from the mean either side. So that's pretty simple here. You just select which latent coordinate you're interested in. Let's go with the 0th component dimension. And we define how many volumes we want it to render. I'm going to say 25. This might take a little bit, and go. And so now what we will do is it will sample through your latent space according to the 0th latent coordinate, or the latent variable. And it will generate 25 volumes along that space, which is something that you can do in cryoDRGN, but at least this way you can sort of interactively look at your landscape and the trajectories that correspond to each of these coordinates. So once this finishes, what it will do is it will plot a trajectory in the space, and it will generate a morph map. So if you don't want it to plot a trajectory, you don't want it to generate the morph map, then you can unselect those, and it will just generate a bunch of volumes that are sampled in order. And if you find that a particular trajectory is interesting but it's going in reverse, then you can select this reverse and re-render it. Okay, so now cryoDRGN has finished generating that volume series. You can see that we have 25 volumes and a morph object. So this morph object allows us to visualize, say, conformational changes along the 0th latent coordinate. And what you can see is Wiggle is plotting here in this landscape a trajectory, and it plots as you morph through this state the position in the space that corresponds to those conformations. So it helps you visually link your latent space and the conformations that you're seeing here in 3 dimensions. You can turn those off to look at other ones. I actually find that it's quite nice to see this with a white background. It's a bit clearer to see where we are in the space. So let me change the color of those, and let me just make them slightly less visible. And so you can see as you drag along this slider, we can see those states. Now if we want to link the volume to the plot, it will allow us to hover over a point which will instantly snap to the conformation sampled at that point. So this is useful if you want to define your own trajectories. So let's reset the state, and we'll close all of those volumes. And this time we'll define our own trajectories. So we have to turn on the select anchor points mode. And here, as we select these points, we'll define anchor points. I'm just going to turn off the continuous update so that cryoDRGN is not rendering volumes at every point. That way we don't have to do it twice. So I'm going to start up here, and I'm just going to randomly at this stage select points through my space to get a sense of what these trajectories might correspond to. Now, the question arises whether these trajectories are meaningful, and really you're going to need to use additional experimentation to validate the conformational trajectories that you might visualize in these spaces, because in the experiment, of course, we don't have any sense of the direction of time or how these clusters are related to one another in terms of biological and physiological sequences. So that may be an interesting point for community discussion, is how can we as a community come up with means of validating these conformational trajectories. Of course, for some biological samples there is a priori knowledge, and that may be the case for the ribosome here, and so I may be just choosing silly trajectories that don't really make sense. But the point is still valid that you can use this to get a sense of how conformational changes take place, but you need to be careful about the claims you make with respect to these trajectories, and it's just a good thing to keep in mind. So perhaps with time-resolved cryo-EM, this will become even more powerful. Okay, so we have our morph map now. We've got our morph object slider here. And once again, now what I have is a volume which is rendered through this space, and you can see for this particular trajectory what we're simulating, or what we're generating there, is the assembly of this ribosome from multiple components. So if I go backwards, we start off with a relatively small component, and then we build it up as we go. And you can see around here, this cluster here, we get the apparition of this additional subunit there. And as we keep going, we tend to build more things onto it. Okay, so that's nice. So this is the trajectory, graph traversal trajectory analysis. I'm not going to go into the minimum energy path analysis. I'll leave that for another video. And particle export currently for cryoDRGN is not available, but that will be available in a future release. That's all for this video.